In this video, we're going to take a look at the homework for extreme value theorem, for Rolle's theorem, and for mean value theorem. So let's jump in. So we're going to begin on page 209, problem number 24. So I'm going to start over here on the right-hand side. In number 24, we have a quadratic function. So we have f of x is equal to x squared plus 2x minus 4, and we have the closed interval from -1 to 1. And our job here is to locate absolute extrema. So we are looking for the absolute max and the absolute min if they exist. So we're going to check the conditions of the theorem. Make sure that you always check the conditions over here on the left-hand side. Conditions of the mean value theorem are: you have a function that is continuous on a closed interval. So that's your condition for applying the extreme value theorem. If this condition is met, then the promise is that there will be an absolute max and an absolute min. So back over here to the right-hand side, in number 24, I have a quadratic function, which I know and you know is continuous everywhere. So it's certainly continuous on the closed interval, so we can apply the extreme value theorem. To apply the extreme value theorem, I'm going to need to identify the candidates. And the candidates are the endpoints, which we have already been given to be -1 and 1. And the other candidates are any critical numbers, which we will find by setting the first derivative equal to 0 or undefined. So I'm going to find the first derivative of f. So f prime of x is 2x plus 2. I'm going to set that equal to 0 to find any critical numbers. Subtract 2, divide by 2, I get x equal to -1. And -1 is already an endpoint, so I don't get any additional critical numbers that are not endpoints. So over here on the left-hand side, I'm going to do my candidates test by making a table. So I have x and I have f of x. Remember, substitute back into the original. So my candidates are -1 and +1. I'm going to substitute -1 in place of the original function. So if I have -1, make sure you put that in parentheses when you're substituting. That's a common mistake that students make. 2 times -1 minus 4, so that's 1, minus 2, minus 4, so that's -6 plus 1, so that's -5. And when I substitute 1, I will get 1 plus 2 minus 4. 1 and 2 is 3. 3 minus 4 is -1. So -1 is the absolute max. The absolute max occurs at x equal to 1. Make sure you get your vocabulary correct. So when you write up a sentence, the absolute max occurs at x equal to 1 and is -1. The absolute max is the y value. The absolute minimum occurs at x equal to -1 and is -5, the absolute minimum value. All right, let's go to number 28. Clear these annotations. And they're gone. All right, looking at number 28, I'll set that up over here on the right-hand side like I did for the other one. So in 28, we have g of x equal to the cube root of x. I'm going to go ahead and write that as x to the 1/3 power. And that's on the same closed interval from -1 to 1. Again, I have to think about the conditions of the extreme value theorem. I know that the cube root of x is a continuous function everywhere. Therefore, it is a continuous function on the closed interval from -1 to 1. So therefore, I can apply the extreme value theorem. I will find an absolute max and I will find an absolute min. I'm going to identify my candidates. And we know that the candidates are endpoints of -1 and 1. and any critical numbers that I might find. I'm going to find the first derivative of my given function, so that's 1/3 x to the negative 2/3 power. That's the same thing as 1/3. I'm going to change that negative power to the denominator, and I'm going to change back to a radical. So that would be the cube root of x squared set equal to 0. Since the numerator is already 1, this fraction cannot equal to 0. However, since there is a variable in the denominator here, if x is equal to 0, the first derivative goes undefined, which makes 0 a critical number and one of the candidates that we're going to test over here on the left-hand side. I'm going to create my candidates test. So I have my x values and my output g of x, substitute into the original function. -1 is an endpoint, 0 is a critical number, 1 is an endpoint, and I'm going to be substituting. Remember, our original function is the cube root of x. Cube root of -1 is -1, cube root of 0 is 0, cube root of 1 is 1. So my absolute max is 1. It occurs at x equal to 1. My absolute min is -1, and it occurs at x equal to -1. And then one more of these, number 34. In 34, we have a function. Let me copy that down. So over here, 34. Make sure you copy the right one. Y is equal to x times, notice I said times, so there's a product rule coming in here. ln of x plus 3 on the closed interval from 0 to 3. Alright, so let's think about this factor by factor. I know that y equal x is a continuous function everywhere, and I know ln of x plus 3 is continuous as long as I take the ln of a positive number. And so if I substitute 0 in here and 3 in here, any of those numbers will give me a positive output. So I am okay. This function is continuous on the given closed interval, so there will be a max and a min. I need to identify an absolute max and absolute min. I need to identify my candidates. I know that the endpoints are given, and the endpoints are 0 and 3, and I need to find any critical numbers, so I'm going to have to find the first derivative. It is a product, so I have x, and I have ln of x plus 3. The derivative of x is 1. The derivative of ln is u prime over u, so here's my u. So that's 1 over u prime over u, x plus 3. So I'm going to multiply, and add. So I get, come down here. So my first derivative is x over x plus 3 plus ln of x plus 3 set equal to 0. Alright, now to solve this equation, I'm going to, let's see, I'm going to need a calculator. So I'm going to pause the video and pull up my calculator, but you won't really notice anything. Alright, so since I can't solve this equation by hand algebraically, I'm going to bring up my graphing calculator here, but to solve this, I'm going to keep x over x plus 3 on the left-hand side, and I'm going to move the ln to the right-hand side and figure out, I'm going to put this in my calculator as y number 1, this in my calculator as y number 2 to see where they intersect. Alright, so I've already done that. So notice in where I have typed these into the calculator, in y1 I have x over x plus 3, and make sure you put that denominator in parentheses. And on the right hand side in y number 2 I have the opposite of ln. I have an extra parenthesis in there, but I don't think it's going to hurt anything. Let's see, I can get rid of that. I just noticed that. Alright, so let's get rid of that. Oops. Negative ln, I'm typing on my computer, negative ln of x plus 3. There we go. All right, so those are our two functions. We want to see where they intersect to see if we have any critical numbers, because that's where the first derivative would be equal to 0. So now I have those in my calculator. I'm going to go to zoom, and I'm going to select number 6 because that's a standard viewing window. And I do see a point of intersection right here, but remember, our interval that we're looking at is from 0 to 3. Sorry about that. That made the calculator go away. This point of intersection is not on the closed interval from 0 to 3, so even though it's technically, by definition, a critical number, that critical number is not on the closed interval, so I am not going to consider it. But yes, this one does require the use of a calculator. All right, so I'm going to put that away. Get rid of this. View browsers. Okay, they're gone. All right, so I don't get any more candidates as a result of that, so I'm going to go to my candidates test over here on the left-hand side. I'm going to substitute, I have my endpoints of 0 and 3. Those are my only candidates, and my function's name is y. So when I substitute 0 here, it doesn't matter what I put in the other factor, because 0 times any number is 0. All right, and then when I substitute 3, I'll have 3, I'll just write it here, 3 ln of 3 plus 3, which is 3 ln of 6. The ln of 6 is a positive number, times 3 is a positive number. Positive is greater than 0, so my absolute max is 3 ln 6, and it occurs at x equal to 3. My absolute min is 0, and it occurs at an x value of 0. Okay, let's go on to Rolle's theorem. All right, page 216, 1, 2, 9, 11, and 15. So let's review Rolle's theorem. So for Rolle's theorem, we start off with the same condition that we had for the extreme value theorem. So condition number 1, I must have a function that is continuous on the closed interval. That's the first thing that has to happen. The second thing that should be true for Rolle's theorem is that f of a is equal to f of b, meaning that the endpoints have the same y value. All right, look at almost forgot my third condition. Well, actually, I like to do them in this order. This would be my third condition. So my second condition that I forgot to include, we'll put a little arrow right there, is that the given function must be differentiable, meaning it must have a derivative on the open interval. Now what that means again is that the function does not have to have a derivative at either of the endpoints, but it must have a derivative at every value of x between the two endpoints. So again, the conditions are, Rolle's theorem is just like extreme value and intermediate value, in that the function must be continuous on a closed interval. Secondly, now we go to calculus, the function must have a derivative on the open interval, and the endpoints must have the same y value. So let's take a look at number 1. So back over here, in exercises 1 through 4, explain why Rolle's theorem does not apply. So they're already telling us this is not going to work. It's going to break one of these three conditions. Even though there exists an a and b such that f of a, so they're telling us right now it's not going to be the third condition. The two endpoints are going to have the same y value. So if we look at number 1, the endpoint, here's the first endpoint, here's the second endpoint, yep, they have the same y value. When I look at the graph, I can see that this function, let's make this, no, we'll just leave it like that. I can see that the function is continuous. There are no breaks, gaps, or holes. But with my calculus eyes, I see a sharp turn right here. And I know that there's no derivative at a sharp turn because the left derivative does not equal to the right derivative. So I would say for number 1, the reason that Rolle's theorem does not apply, number 1, Rolle's does not apply because the function f of x, I'm going to make sure I say the specific name, is not differentiable at x equal to 1. And that's all I have to say. If I break one condition, it doesn't matter. We cannot make any promise that the derivative, and remember the promise of Rolle's theorem is that somewhere the derivative will be 0. It still might happen, but I can't promise it by Rolle's theorem. Okay, number 2. So when I look at the graph with start with algebra eyes, I can see that this function is not continuous. Right away I see a vertical asymptote here and a vertical asymptote here. The closed interval, they're highlighting the point at pi and 3 pi, and on that closed interval, that given function f of x is not continuous, so Rolle does not apply. So I would say number 2, Rolle's theorem does not apply because the function's name is f of x is not continuous on the closed interval. Notice I'm being very specific. I didn't say the words closed interval. I said what specific closed interval from pi to 3 pi. Now I could have used number 2 since f of x is not continuous on the closed interval. This function is not continuous at 2 pi. Therefore, the function is not differentiable. But it doesn't matter. If I break one condition, it doesn't matter which one I claim. As long as I claim to break one, the promise is not guaranteed to be fulfilled. All right, in number 9, we are looking at a function. So here's endpoint number 1, endpoint number 2. So in this one, I'm not sure these were the directions for 1 through 4. So I think in number 9, we're actually supposed to figure out the value guaranteed by Rolle's theorem, because I can see that I have endpoints with the same y value, condition number 3 met. I can see that I have a function that is continuous on the closed interval. It's differentiable on the open interval. Therefore, Rolle's theorem applies. All right, so to apply Rolle's theorem, remember the promise of Rolle's theorem, if all 3 conditions are met, is that somewhere there will be a value of x called c, where f prime of c, the derivative, is equal to 0. So I'm going to figure out where that is. So f prime of x is equal to 2x plus 3. Set that equal to 0. And I get negative 3 over 2. Oops, come on, Jernigan. I'm already one step ahead in my head. There's the eraser. Okay, set that equal to 0, and x is equal to negative 3 over 2. So that is the value of c, guaranteed. So there is a value c. In this case, it's negative 3 halves. Where f prime of c is equal to 0. So f prime of 3 halves equal to 0, and that was the promise by Rolle's theorem, that somewhere on that interval there will be a value of x where the derivative is 0 if all 3 conditions are met. All right, let's clear these annotations and do number 11. Same thing going on. So in number 11 we have x squared minus 2x on the closed interval from 0 to 2. X squared minus 2x is quadratic, so it's continuous everywhere. Therefore, it's continuous on the closed interval. I know that a quadratic function is differentiable everywhere, so 2 check marks, and differentiable on the open interval. Now I need to find out if f of 0, so if I substitute 0 in place of x and 0, I get 0. And then f of 2 would be 4 minus 4, which is 0. So check. The endpoints have to have the same y value. They don't have to be 0, but they do have to have the same y value. So therefore, the promise is somewhere the derivative will be 0. So the derivative is 2x minus 2 set that equal to 0, and x is equal to, add 2 divided by 2 is 1. So the value c that guarantees the derivative will be 0 is an x value of 1. So that's the promise fulfilled by Rolle's theorem. And then lastly, number 15, x to the 2/3 power minus 1 on the closed interval from -8 to 8. You might have to take a quick gander yourself with a calculator, but x to the 2/3 power is a continuous function. It's just being shifted down 1 unit, so it's continuous everywhere. Therefore, it's continuous on the closed interval. X to the 2/3 minus 1. Now, we have to be careful because x to the 2/3 power is our bird function. So if you take a look at this on your graphing calculator, shifted down 1 unit, it will look like that. And so that's going to be a problem. So I'll confirm that for you by looking at the calculator since I have it pulled up right here. So I have x raised to the, I like to put my fractions in parentheses. I think maybe on the newer models sometimes you don't really have to do that, but I like to. And then minus 1. I always start with the standard viewing window of zoom 6. And so we see a cusp happening on our function, and so we know that there's no derivative at x equal to 0. And 0 is on the closed interval from -8 to 8. So I would say Rolle's theorem does not apply because f prime of 0 is not defined, or you could say f is not differentiable if you wanted to use the specific words at x equal to 0. So Rolle's theorem does not apply. All right, so that's your Rolle's theorem practice. Let's go to the mean value theorem. All right, we're in the same section, but we have a different concept now. So let's review the conditions of the mean value theorem. So the mean value theorem, condition number 1, just like every other theorem, the function must be continuous on the closed interval. And make sure you don't know these conditions until you can write them yourself without looking at anything else. The function must be differentiable on the open interval, so just like Rolle's theorem. The only difference here, though, is for the mean value theorem, the endpoints do not have to have the same y value. So mean value is different, a little bit different from Rolle's theorem. I will tell you this, however, wherever you can apply Rolle's theorem, you can apply the mean value theorem. The important part of the mean value theorem is understanding the promise. So if the conditions are met, the promise is somewhere on that interval, the average rate of change, so that's one of your jobs. You have to calculate average rate of change by calculating slopes, that's your Algebra 1 piece, is equal to the instant rate of change, and that is the derivative of the function. So that's the work that has to occur. All right, let's look at number 35 through 36. Copy the graph and sketch the secant line to the graph through the points A and f of A and B f of B. Then sketch any tangent lines to the mean value theorem for each value of C. All right, let's see if I can do this with my software here. So I'm going to insert a shape, and I'm going to grab a line. Let's see if I can get a secant line from A to B. So here's A to B. Okay, that's pretty good. Remember, secant line goes through two specific intentional points. So that's my secant line. I'm going to copy that because I want to make a line that is parallel to that. So copy and paste. All right, let's see if I can grab it. There I did. And I'm going to change that color to red. So remember, the mean value theorem says somewhere the instant rate is equal to the average rate. Well, let's come back, let's move that line over here. So the instant rate of change, this is a really good review. The instant rate of change, grab my pen, change that. I didn't mean to change that to a white line, but whatever. So that is, the instant rate of change is slope of the tangent line, and the average rate of change is the slope of secant line. And if they're going to have the same slope, then those two lines have to be parallel because they will have the same slope. Okay, so that's the big idea. Let me come back over here and change this line back to a red line. And because I copied this line, it's certainly going to be parallel, so I'm going to slide it until I am tangent, which is about right there. So at this value of x, let's see if I can do something here with that. All right, so at this value, approximated, this is just eyeballing, whatever this, we'll call it c, whatever that value of c is, that's where the instant rate of change is equal to the average rate of change. All right, let's do it again for number 30. Well, let's go ahead and talk about 37 and 38. No, they're different situations. Okay, so let me draw my line, my secant line. So that would be the slope of my, slope of my secant line would be average rate of change. So insert shapes, grab my line. All right, I'm going to draw a line from A to B. Pretty close. Let's see if I can adjust it just a tad. Probably make a mess of it. Better, a little bit better. Okay, we'll call it. All right, so the blue line is my secant line, and I'm looking for a line parallel to that. That's tangent. So I'm going to copy and paste. Oh, those are tight. Let's see if I can grab the right one. Yes. Okay, and I'm going to change that to red. And I'm going to put it on top of my secant line. And I'm going to slide. And so, whoa, there is a value of C. So notice that that red line is tangent, but I'm pretty sure that there's going to be another one. So I'm going to copy and paste. Oh, they're so close to each other. Another line. Because if I go back to the original and I keep sliding, there is another place where the tangent line is parallel to the secant line. So in this case, there are two times where the mean value theorem is true. So this is just a visual representation. So at this particular value of x right here, we'll call it C, and at this value of x right here, we'll call it D. The instant rate of change equals the average rate of change. For 37, they're telling us straight up the mean value theorem does not apply, so we have to go to conditions, and right away I can see that this given function is not continuous on the closed interval, so the mean value theorem cannot guarantee anything. In 38, my eyes go directly to a sharp turn, and so there's no derivative at that sharp turn. Therefore, I would say that f of x, or whatever the name of this, f of x is not differentiable, specifically at x equal to 2 or on the interval. Therefore, the mean value theorem does not apply. Conditions are not met. And now we have 35 to 38 all, and 43, already did 35 to 38, 43 to 49 odd. So 43, 45, 47, 49. So I'm going to do one of these that's pretty directly algebraic, and then maybe one that's not. I'm not going to do all of these. So I'm going to start with, let's clear that. That's a mess. Clear the annotations. So circle them carefully, Jernigan. 43, 45, 47, and 49. I'm going to do 45, and I'm going to do 49, and then you can use the solutions manual to support you with the other ones. All right, so over here on the left-hand side, number 45, I have the function f of x. Notice how I copy it is equal to 2 minus x to the 1/2 power. This is a square root function. It opens to the left and it is shifted to the, let's see, careful, to the left 2 units. Let's grab our graphing calculator to make sure of that, because we want to make sure that we have a function that's continuous on the closed interval and differentiable on the open interval. So clear, and we're putting in square root of 2 minus x, standard viewing window of zoom 6, shifted to the right. What did I say? Hopefully I said to the right. The closed interval is from -7 to 2, so yes, I can see visually this function is continuous on the closed interval. There's a derivative everywhere, so we are good to go. So the 2 conditions are met, therefore the promise can come true. So remember that the mean value theorem says the average rate of change is equal to the instant rate of change. So first, I'm going to find the average rate of change. So I'm going to need the x and y coordinates. So I have -7 and I have 2. Those are my x coordinates. I'm going to substitute into original function to get the y coordinates to go along. 2 minus -7 is 9, and the square root of 9 is 3. Substituting 2 minus 2 is 0, and the square root of 0 is 0. So the average rate of change calculated is y2 minus y1 over x2 minus x1. So that's my average rate of change. Check it, 6 minus 3, 2 minus -7. Okay, over here on the right-hand side, I'm going to do my instant rate of change. Instant rate of change is derivative. So f prime of x is 1/2 of the quantity 2 minus x to the -1/2 times, don't forget the chain rule, -1, derivative of the inside. So f prime of x, before I bring it over, I'm going to move things around. So the -1 in the numerator, 2 in the denominator, and notice I'm taking the negative power to the denominator and changing it back to a square root because I got to do algebra work. So I'm going to bring that over here, -1 over 2 times the square root of 2 minus x. So I have to solve for x. 6 minus 3 is 3 over 2 minus -7 is 9, equal to -1 over 2 square root of 2 minus x. That is 1 over 3 equal to -1 over 2 times the square root of 2 minus x. So I'm going to cross multiply, and I'm going to bring that over here into the white space. So that'll give me 2 square root of 2 minus x, cross multiply. 3 times -1 is 3, cross multiply. That's square root of 2 minus x. I'm dividing both sides by 2. Squaring both sides gives me 9/4. Bringing it up here, subtracting 2 from both sides. If I subtract 2, that will be 8/4. 2 is 8/4. So that gives me -x equal to 9/4 minus 8/4 is 1/4. Divide by -1. So x equal to -1/4. So when x equal -1/4, the average rate of change is equal to the instant rate of change, and so that is the value of C guaranteed by the mean value theorem. So that was a good one to do for you. And let's take a look at number 49. And finally, number 49. So in 49, we have a trig function. Sine x, it's right here. Sine x is continuous everywhere, so yay. It's differentiable everywhere, yay. So we have met our conditions. So the promise is true that the average rate of change will equal the instant rate of change somewhere. We just have to figure out where that is. So to find the average rate of change, I'm going to need to take the x coordinates of 0 and pi and find their y coordinates by substituting into the original function. The sine of 0 is 0, and the sine of pi is also 0. And remember, sine is the y value. And so the average rate of change would be change in y, 0 minus 0 over pi minus 0. And that's just going to be 0 over pi, which is 0. So that is the average rate of change. Over here on the right-hand side, the instant rate of change, f prime of x, the derivative of sine is cosine. Now the promise is the average equals the instant somewhere, so I'm going to set the average rate of change, 0, equal to the instant rate of change, cosine of x, and cosine, the x value, or cosine is 0 at pi over 2, because we're on the closed interval from 0 to pi. And so pi over 2 is the value guaranteed by the mean value theorem, where the instant rate of change is equal to the average rate of change. So that's your homework. Hope it helps.